Thank you so much.
Thanks. And thanks for coming, guys. So I'll tell you about a couple of, I'll tell you about the set cover problem, and I'll tell you about a couple of new algorithms. Actually, I'll tell you some old algorithms as well. But you might think that set covers are well picked over area. What else can be new? So there's a couple of new things that I can tell you about. And it's kind of fun, and this is work with several students, ex-CMU, but now at various places, Greg Kehne and Roie Levin, and another paper with Euiwoong Lee and JCP. Okay, so all the papers are on the archive, but I should put up the links at some point, but you can find them on my webpage. Okay, so most of you, I guess, know what the set cover problem is. You're given a bunch of sets, a set system, and there's some underlying elements, in this case 6 elements, and there's some number of sets, and I'll usually denote n number of elements, m being the number of sets, and you want to pick the smallest collection of sets to cover all the elements. So in this case, these 3 sets cover all the elements. Okay, and there's also a weighted version of the problem where sets of costs, and you want to minimize the cost of the cover. Okay, so you guys know what set cover is. Please feel free to ask questions. I work best on questions. And usually it'll be most convenient for us to think of this as being this bipartite graph, essentially. There are a bunch of sets, there are a bunch of elements, an edge between a set and an element. If the element belongs to the set, you want to pick the smallest collection of sets that cover all the elements. That's good. Okay. So, I mean, this was a set cover, but this happens to be the smallest set cover in this case, and you can check that every element belongs to one of these red sets. Good. So, old problem, one of Karp's original problems. I was trying to find, what was the oldest reference I could find, but maybe 1971 there was a reference, but I'd love to find out older references for set cover. It's kind of fun to find out these things. But by now, there are entire courses. Ulla Svensson is right now teaching a course. If you want to learn all about set cover, you can see almost all the standard techniques in algorithm design. We are using set cover to solve to illustrate these ideas. Okay, not important what this is. But in any case, what I'll tell you about is I'll tell you about local search algorithms. Well, actually, let me tell you what I am going to tell you. So previous results for set cover, this notation, n elements, m sets, each set has size at most b. Yeah, I have no idea why this thing's becoming fuzzy, but hopefully you guys can error correct. We know logarithmic approximations. We know essentially harmonic number of b times opt. Opt is the size of the optimal set cover, or the weight of the optimal set cover. Okay. And I know how to approximate this up to a factor of h of b. The problem is NP hard, and this is the best approximation we know. We can do something better for unweighted systems, but maybe, let me not bother you too much with things. The point I want to tell you is that this is pretty much tight. So in polynomial time, if you can do better than log b, pretty much the upper bound, minus a log term, then p equals n. Okay. So this problem is pretty much solved. One thing we don't know is this factor out here. Where is the truth of the situation? Okay. But pretty much log approximations are the best we can do, and log approximation is what we do. Okay. Good. So what am I going to tell you about? So since we know many ways of getting a log, I'm going to tell you how to get it using local search. But more than, just, so the approximation will be log b minus a tiny bit. It's minus a little smidgen out here. People are interested in this because if b is like 3 or 4 or something like this, and these arise in other approximation algorithms, the improvement you get here is actually matters. Okay. I would love to show h of b minus 1, let's say, or h of b minus a half, let's say. Actually, h of b minus a half would be really interesting because when b is 2, this problem is known as edge cover and is reducible to matchings. So it's in polynomial time. H of 2 is 3 halves. 3 halves minus a half would be 1, which would be right. So morally, h of b minus a half would be, I would believe, really well. I don't know how to do that. I know how to do something, minus the 16th. Okay. Not the greatest, but at least some progress. It's the first non-trivial approximation I can show using local search. So it's a new idea. And I'll show you an interesting, cute little thing that you can do. And it improves on some previous result by Roie Levin and Asaf Levin. Okay, good. So I'll show you local search. And I'll also show you a different model where elements arrive in random order. It's interesting in an online model if you haven't seen this before. And I'll show you a log approximation. The actual performance is slightly worse, but the math is somewhat interesting. I'll show you something more.
Is some hardness of approximation for b constant b? So assuming some EH or something.
Good. So actually, for constant b, you can still get a lower bound of log b minus log b. That's pretty much. So the assumptions might not be p equals np. It might be np is not contained in some pseudo polytime. But yeah, there's a paper of Luca Trevisan which shows that. Yep. Good. So today's plan, basically I'll show you a little bit. If you haven't seen these things before, chances are you guys have all seen algorithms for set cover, but it's always good to warm up a little bit. And then I'll show you a local search, and then I'll show you something about this online. Okay. Good. So far, so good. Okay. So the greedy algorithm is, what you try. You start off with the universe of elements. And at any point in time, there's some set of elements. Think of U as being uncovered. So there's some set of elements which are still uncovered. You pick the set that maximizes the number of uncovered elements being covered. Now you add this set to your collection, you remove this, you cover these things. So the uncovered uncovered elements are these, and you go on from there. Okay. And so you're actually maximizing the number of uncovered elements that are being covered by the set divided by the cost of the set. So in general, you're looking at the Banford buffer. And proof for the unweighted case is one that you teach in your undergrad algorithms course, right? So, at every point in time, the entire universe can be covered using, let's say, opt many sets. This is only for the unweighted case. The weighted case, the proof is slightly more complicated, but not really. So, the whole universe can be covered using k sets. So clearly this orange region can be covered using k sets. So the best one you'll pick will, the best set that you'll pick will cover at least 1 over k fraction. It's an averaging argument. So the number of uncovered elements drops by 1 minus 1 over k. How many times can you do this until you drop the number of elements from n to 1? It's k log n. Just that simple. Okay. So up towards k, you are k log n, and that's log n. And the greedy algorithm is tight. You can't do much better than this. And in fact, no algorithm can do much better. Good. So let me tell you a local search. I'm not showing you, the 50 other ways in which we can solve the set cover. I'm just showing you the new stuff. And it's also very simple. Okay. So local search, start off with any solution and then perform any local move that improves the cost of the solution. And so, for instance, here's the local move. Take a set from your solution and drop it. and add a new set. Or take at most one set from your solution and drop it and add at most one new set. You of course want to maintain coverage. And in fact, the annoyance was for the longest time, we didn't know of any local search algorithm for set cover. Now, what is a local search algorithm for set cover? So the naive thing could be, just try to implement this. And if you think about this, this is a really crappy algorithm. Because imagine the following situation: your current solution looks like this. There's one set that covers all the elements, but there's a beautiful solution, these yellow sets, which cost 1 each. So there are n of these, they cost n. The red set costs a lot. So you want to move to the yellow solution. But if you are at the red one, what can you do? You can't drop the red unless you add all the yellows. And adding all the yellows could be pretty expensive. I mean, it's basically like solving a set cover instance. So this, once you see this example, you say, well, what can we do? We seem to be, local search maybe not the greatest algorithmic idea for set cover. So what I want to convince you is that, no, maybe you should think outside the box. And how do you think outside the box? So this is perhaps the one idea I want you to take away from this. Why do you always want to just improve the cost of the solution? I want to introduce an idea of a surrogate, cost, a potential. And I just say I'm going to define a potential and just improve the potential. And the potential can be related to the cost, but not equal to the cost. That's all. And that's the main sort of philosophy. The rest is details. And I'll tell you a potential which works in this case. It's also a cute little potential, also an old potential. Okay. So this idea of non-oblivious local search is something that people have been, Sanjeev Khanna and others defined it in '98. And over the past 10 years or so, I think it's been very popular for a bunch of problems. So you might find it useful. Okay, so let me just tell you the potential. So here's the potential. So the potential says, given a solution, its potential is equal to the cost of the sets in the solution times the size of the set, times the harmonic number of the size. So larger sets are causing me more grief somehow in the potential. I mean, obvious facts. This potential is the upper bound on the cost, but not too much more by this log factor. And now my algorithm is just going to be start off with a solution, any solution. And if there is a move that improves the potential, just one set. If you can add a set to your solution that improves the potential, do it. With this, one catch. We'll see. So far, so good. Okay. For simplicity, just imagine that our set cover is closed undertaking subsets. It's downward closed. So if a set belongs to your system, a subset belongs to your system. You only worry about this for poly time, and we can take care of this, but this is a talk. Okay. So what's our local search algorithm? I'm starting off with a solution belonging to this downward closed subsets. That's why I put this downward. Our potential is that. Okay. At each point in time, I can assume that my solution is a partition of the space. Because otherwise I can always drop the repeated elements, my potential always is. Okay, so my solution looks like this.
The cost of subsets are related to the cost of the big set?
Yeah, so the cost of the subset is the same as the cost of the big set.
Okay.
Absolutely. Good. So I have a partition of the space. Good. And now all I'm going to do is, if there exists a new set T, which is not in my solution, such that adding it to my solution, and when this T is added in, it captures all the elements from all the other sets. Okay. This new solution, if it has smaller potential than my original potential, move to this. The obvious thing. One thing to note, by the way, is that if T captures all of some set S, then you can drop that set, of course. So in some sense, the empty set is the only one which doesn't inherit the cost from the upstairs. Its cost is 0, obviously. And because I did this removing all the elements of T, I maintain a partition. Okay, that's it. In case you're wondering, what's the catch in this algorithm? There is no catch.
Maybe you don't want to go into, but yes. Why is allowing the subsets to also be in your family doesn't change the problem like significantly?
Yeah, so really what I could do is I could just say that, look, I'm just going to, I'm going to keep the original sets. And then for every element of the universe, I'll keep track of one of the sets that covers it.
And when you cover everything, you drop it.
Exactly. Oh, exactly. So it's pretty much the same. It just makes my explanation a bit easier. That's, yeah, you're spot on. Good. Okay. And okay, so that's the algorithm. I'll move the algorithm to the side. And I'll show you the following thing, that local optima for this local search are good. We'll worry about the polytime aspect of it. Okay. So I want to claim that if S is a local optimum, then its cost is at most the cost of any other solution. In fact, the optimal solution times H of T. Okay. And the proof is going to be, there's going to be a Helmholtz square out there. It's just this, right? You should teach it in your next algorithm. Okay. So here's what I want. I want to compare my solution to opt. So one thing I know is that for every set in the optimal solution, adding it cannot improve my cost. Maybe it'll keep the cost the same, but it's not going to improve my cost. Oh, sorry, improve my potential. Okay. So let's look at the change in potential. It must not improve. What is the change in potential? Adding T increases, there should be C of T, cost of T, not weight. Okay. It introduces this term in the potential. But for every other set in S, it changes the term to this much. All the sets in the intersection, all the elements in the intersection have been dropped. Fair enough? Let's look at this part. My claim is each of these things is at least, it's really 1 over S plus 1 over S minus 1 plus 1 over S, whatever. Each of those marginal improvements is at least this much. Fair enough? This is true for every set in opt. So let's sum over all the sets in opt. This term, summed over all the sets in opt, is exactly the potential of opt. And this, summed over all the sets in opt, the summation over all the sets in opt just moves over to the other side.
Isn't it log of the? It's like log S minus T.
Right. So, so it's exactly log s minus t, but I think we're using the approximation that log of, so how should I see? So basically all I was saying was this, that this was 1 plus 1 over 2 plus 1 over s minus t plus 1 over s minus t plus 1 all the way to 1 over s. This was my original potential. Now these terms have dropped. And each of these terms is at least 1 over s. Okay. And there is s intersect t of these. It's somehow doing algebra on the board is always, yeah. And then I summed over all the sets in opt. Now note that s intersect t summed over all the sets in opt is a cover. This must be the same as the size of s, at least the size of s. So this term is going to give you at least the cost. I mean, this expression is going to be at least 1. So this is going to be at least the cost of s, which will be at most this potential of phi. But the potential of phi is at most the cost of, the potential of s star is at most the cost of s star times log. So my cost is at most cost of log times log. More or less, what's happening is this potential, if you drop an element, it's like improving by exactly the cost divided by s. So every element, the derivative in some sense, is like its cost share of the solution. And that's why this potential is very useful.
So how do you go from a general instance to the one that you have closed downwards? Because you might have very small sets that have much smaller weights than larger sets.
Good, right. So the important thing is that the cost of a set, which is, so if I took a large set and if I took a smaller, a subset of it, I'm keeping the cost to be the same.
Right.
But the potential is different.
Right, but the general instance of the original problem does not have that.
Does not.
But you could, at least you could try to close it downwards sort of artificially by saying, okay, every time I have a set, I imagine that I also have all its subsets with the same cost. But if you already had one smaller one with a different cost, that
right. So then there might be several sets of a small, of smaller size.
Smaller, but smaller
you take the one, you can keep all of them.
Right, but then you have to be slightly careful with the potential thing, because sometimes you remove some set and you land on a place that you could actually have changed the set.
Exactly. But if you work through this, you'll realize that you're actually you're only gaining in that case.
Right. So then, are you saying that the proof just works?
The proof just
look at it.
You just
okay. Good.
And in fact, here is one thing you could do. Just to you could keep many sets of you could keep multi sort of
the idea I was having in mind is that you should have actually a multi-set thing.
Absolutely.
And it just works.
It just works.
Okay.
Actually, does it cost you in terms of the running time? Do you actually need to keep all of these subsets of every set in your original input?
No, in fact, you don't. What you could do is you could just keep your original instance, and for every element of the ground set, just keep track of which set is covering it. And so implicitly you are keeping track of you're keeping track of a subset of the original set.
Yes, but when you are looking for a local change, is it clear? Is it clear that you can do it without looking at subsets of everything?
So all the subsets are differences from things that you're removing. So you don't actually need to add them to your family, I think.
Exactly. So in fact, all you need to do is you need to check only the sets of opt, which are elements of the original ground set. So all the tests moves I'm doing are with respect to the original ground sets.
Okay, so you're saying that when I'm doing the local steps, I actually don't need sets from this downward closed.
Absolutely.
Superset just from the original sets.
From the original sets.
Okay.
And all these are sort of absolutely issues that you should worry about, but all these work in the right direction, thankfully. So the algorithm is basically, you keep a solution, don't worry about intersections, but for every element of the ground set, just keep track of some element, some set that covers it. And whenever you want to bring in a new set, that new set eats up all its elements, and all the remainder just inherit whichever set is covering. So all this can be done in time polynomial in M and N. Other questions? Very simple algorithm, and actually very simple analysis, I feel. Good. You can do, so finding a local optimum might take you some time, because who knows how long it takes to actually find a local optimum. If the weights were 1, then of course every time you improve by 1, and you can show that the running time is polynomial. If you had general weights, who knows? But here is a standard trick that you can do. You can say, okay, start off with a solution of cost which is not crazy, which is, let's say, n times the cost of the optimum solution. How would you do this? For every element, pick the cheapest set that covers it. That's cost no more than opt. So that's n opt. And now let's say make moves only if the potential drops by a significant factor. And now you can sort of play around with it and show that, well, if you reach a local optimum, then the local optimum should not cost you all that much. You'd have to rework the previous analysis, but it's a small amount of extra. So as long as you're happy with a fudge factor of plus epsilon in the approximation, you don't need to worry about runtime. The runtime is something like this. And of course, you could say, oh, can we get a poly of m, n, and log 1 over epsilon? And those questions then become hard. They start becoming related to these questions of, oh, the complexity of local search algorithms. Can you find a local max cut fast? Can you find a local solution to this fast?
Well, why don't you start with the solution of log n opt from the greedy?
Sure. So, but if you start with the log n opt, then you're, for this approximation factor, maybe there's nothing more to show. So, but yeah, this is from first principles. But you could start with whatever. In fact, one of the things that we don't tend to do in our approximation algorithms is we often don't tend to do like local search at the very end, which when I talk to people in practice, they complain, oh, your solution is not even locally optimal. So maybe, yeah, we should have this as a post-processing to any algorithm.
Is it obvious that if you started from a solution and you did your post-processing, you would clearly improve the potential? Is it obvious you would
improve the cost? Not clear.
Okay.
Good. Okay. Minor thing. If you were really interested in this sort of technical question of getting strictly better than h of b, then you can ask the question, what if I add and drop 2 sets at a time? Or whatever, add 2 sets at a time and drop whatever. So if you add 2 sets at a time, you can get a slight improvement over what I just gave you. And then you can start playing, oh, is this the right potential? Then you can play with the potential and get this kind of behavior. So this is what I can show right now. I can show if your b is, let's say, 3, then I'm showing, whatever this is, 1 plus 5/6 minus a little smidgen. And remember, if I could just make this 1/2, I'd be very happy. But I don't know.
If you do two at a time, it's like a quadratic time. You have to try all.
You have to try all possible. Yeah. So the running time goes through the roof. But, good. Yeah. Okay. Yeah. So can I get something which is better by half? Something which goes better with some factor which depends on B. Anyways. Good. Okay. So I showed you this local search algorithm. It's cute. It's not. It's a first step towards trying to get even tighter approximations. Okay. One more thing to mention, by the way. And this goes back a long way, but suppose I don't have a dependence in B. I'm just looking at n. Log n is what follows from log of B. For the unweighted problem, the greedy algorithm is log n minus log n approximate. This is an old paper of Peter Slavic. So the unweighted problem has a log n minus log n approximation. And I think I don't remember if the hardness also holds for the unweighted log n minus log n. We'd have to check that. But for the weighted problem, log n is the best. Sort of quantitative gap between the unweighted weighted problems. Out here. So it's fascinating. It's just we're getting deep into it's only for the specialists minus log n thing. Maybe this room is just right. Okay. So given that, let me in the sort of next half an hour tell you about a slightly different problem, a different model, in fact. And I'll give you another algorithm, which I personally find very cute. And yeah. Okay. So for this, I hope some of you have seen this notion of online algorithms. Here's what's going to happen. The elements are going to arrive one by one. Okay, and I'll explain to you in the next slide exactly the model. And whenever an element arrives, you have to pick a set that covers it. So now you don't see the entire solution, so you can't run the greedy algorithm, for instance. The first element arrives, you have to pick a set that covers it. The second element arrives, and so on and so forth. You want to minimize the cost of the sets picked. And your measure of goodness is this competitive ratio. It's the cost of your algorithm on an instance over the cost of the optimal solution for that instance, worst case over the instances. Okay, and you want to minimize the competitive ratio. Okay. So the first element comes in. So initially, you just know some sets. You don't even know what elements belong to what sets. Just these are hollow shells.
You know their processes.
You know their process. And the first element comes and says, oh, I belong to all three sets. Which one do you want to pick? You'll say, well, I don't know anything. Maybe I'll pick S1. And maybe the second element comes and says, well, I only belong to S2 and S3. And so on. You can see it. So in this particular case, the optimal solution was 1. And you pick 3. And you might imagine, what can I do? Maybe every time you'll make me pick a new set. But then you have to ask the question, what's the optimal cost of this instance?
You're not allowed to drop sets.
You're not allowed to drop sets. Thank you. Yeah, if you're allowed to, that becomes a dynamic set cover problem, slightly different.
Yeah, I was wondering if you're allowed to drop only one set.
Exactly. And in fact, we can talk about this offline. There's some interesting questions out there as well. But in this case, you're not allowed to drop sets. Model clear, right? Okay. Okay. So really, what's happening is, in the bipartite graph world, it's very clear now. An element arrives, it shows you its edges. You have to pick one of the sets that covers it. The next element arrives, you have to pick one of the sets that covers it. Oh, this element arrived. Yeah, you managed to have picked one of the sets that covers it. It's okay, etc. The fifth one, oh, you have to pick a set that covers it, so on and so forth. But online set cover. And this was studied in this paper of Noga and others, Alon, our Bokazar, Bukwinder now. And this paper has been surprisingly sort of late. I would have said 2003 is fairly late for a new sort of problem definition. But it's been very influential. It's led to a lot of interesting developments in online algorithms. So, okay, what is known? I was meaning to, I thought I had it on the slide, but you'll see in a moment. So, I'm going to tell you yet another algorithm for solving set cover. I'm sorry, there's a lot of algorithms for solving set cover coming your way. But all of these are very natural, I would say. So here's one called a technique called relax and round. And it's a two-stage algorithm. And oh, by the way, I'm showing you offline, then I'll show you online. So what's offline? You write an LP relaxation for this problem. And this is an idea that is familiar to many of you. Recently, in fact, what talk was I saying? Oh, the stuff on the Kahnke-Lie conjecture. We're talking about fractional thresholds, integral thresholds, same idea. Right? I'm writing an LP relaxation for this problem. Fractionally pick sets so that every element is covered by at least one of the sets. Okay. This costs no more than opt. It's a relaxation. And now, solve that thing, pick a set with probability XS. Its expected cost is exactly the cost of the relaxation. And a simple chernoff bound. In fact, you don't even need a chernoff bound. Simple calculation shows that every element is covered with constant probability. And so repeat log n times and take a union bound of elements. So the expected cost is like order log n. Okay, this is offline. Online, there's going to be one change. I'm going to solve this LP relaxation online. So the constraints of this LP are going to come one by one. An element comes and it'll add a constraint to this LP. And I need to solve this LP online. I have to round online as well, but this rounding online can be done easily. I'll give you a little cartoon out here. Solve the LP online, round online. Solving the LP online requires a little bit of work. In fact, in some sense, that's one of the main ideas of this paper. And the rounding online is also is kind of slick. At every step, it says, oh, the solution increased by so much. So here we will make sure that the X values only increase. And here in the rounding, we'll make sure that whenever in the ith round, we'll round proportional to the changes. And if you're not seeing all the details, don't worry, you're not meant to see all the details. Right? So take a set with probability proportional to the increase, to the blue portions. And really, what you should think of is this loses log online, this loses log offline, nothing. It's a union, it's a just Chernoff bound, union bound. This part, offline, we can solve LPs exactly, online, we lose log. And actually, it's instructive to see why we lose a log. So let me show you. I want to solve an LP online, and I'll lose a logarithmic factor. So here's an LP. X1 plus X2 plus XM. This is my first constraint. What do you want to do? I'm going to give you more constraints later. What's your best bet? How should you solve this?
All equal.
All equal, right? My next constraint is going to be X2 plus XM. So this 1 over M that you put on X1 was useless. And now you'll again, spread it all equally, and then maybe I'll drop X2 and x3 plus xn is at least 1. So this upper triangular matrix that I'm giving you. And of course, the element I'm dropping is always a random element so that you can't guess it. So you're losing 1 over m minus 1 all the way to 1, you're losing h. So online, if you're solving LPs, you have to lose a log factor. And what they show is that you can lose a log factor and solve this. And that's the kind of the cute idea behind this paper, or one of the cute ideas behind this paper. So you lose a log here, you lose a log there, you lose 2 logs.
There are assumptions for you to solve arbitrary LP online.
Good. So what we know is that as long as the LP is a covering type LP, that is all the coefficients on the left-hand side are positive.
Right, and then you only are going to increase.
You're only going to increase.
Yeah, I see.
And then you can get a log m, log of the number of constraints. General LPs, I think you're pretty much dead.
Yeah, it's
That's what that thinks, exactly. Okay. Log and log, 2 logs. How do you solve the LP? There's some multiplicative weights action going on, but slow me. I mean, I'm not going to tell you about this. Like me, there's only so many ideas I can throw at you during one talk that it's fair to throw at you guys. If you're interested, we'll talk about it later. There's some primal dual action. It's very cute. I love this. Okay. So what do we know? 2 logs, log m, log n. Can we do better? Sadly, there's a lower bound. There's a lower bound. I'm cheating slightly. There's like lower order terms that are floating around, divided by log terms, but I'm not worried. So they showed that for deterministic algorithms, you can't do much better. Later on, Uri Feier and his master student Shimon Korman showed that for polytime algorithms, you can't do much better. Actually, we don't know whether randomized exponential time algorithms can do better. It's a problem. Yeah. So the question that, you had a question? No. So the question that we were interested in is the so-called beyond worst case model. And this gave a new algorithm, which might be interesting by itself, but okay. So here's the question that we asked. Suppose the adversary fixes the instance, but now the elements come in random order. So the first element comes, and then maybe some other element comes, and then some other element comes. Maybe we can do much better. Because in the online model, the hardness is coming from both the instance and the ordering. So we wanted to tease apart these 2 sources of hardness. And this, the sort of motivation for this goes back to the so-called secretary problem. You guys have seen the secretary problem. Nowadays, everybody's seen the secretary. And numbers, you want to maximize the probability of picking the max. In the worst case, you're dead. And in the usual example, I'll give you a bunch of increasing elements, and then it falls off the cliff. So you have to guess which is the highest element. You're basically randomly guessing. But if the elements arrive in random order, you kind of learn a threshold and pick the maximum element with probability 1 over 3. And so people had been asking, can we do better for other online problems in this model? And since the 90s, people looked at this. And for many problems, we knew how to do better in random order. But for set cover, somehow we were failing.
Okay, so that I understand the model. The idea is that you want that there's a random order and you want to get good values with high probability or something. Or
let's say expectations, in expectation. So the adversary fixes this bipartite graph.
Right, but you don't know it.
You don't know
you
it.
need to get it with good expectation. You should get
Absolutely. And yeah, so the right-hand sides are now revealed in random order. You want good expectation. And you can view this as an offline problem solving strategy. This has nothing to do with online. You could just say, well, I want to solve set cover. I'm just going to run this algorithm. Right? The randomness can come internally from my own. Okay. Ignore these things. So I'm going to give you an algorithm which is going to have expected cost order log of mn. Not so good when m is very large, but there's some lower bounds. So this algorithm, okay, good. So let me tell you an algorithm which with two caveats. It'll only work for unit cost sets, and it'll work in exponential time. We'll remove these things later on, but and this algorithm, I'll analyze it completely. In fact, we'll analyze it just on this slide. I love these one slide algorithms. Good. So what's the algorithm? Actually, there's one more caveat in here. Let me assume I know the size of opt. Again, I can get rid of this. But suppose I know that opt has k sets in its solution. So now imagine, remember you have m sets, opt contains k of them. So the way I always think of this is that these are all the possible m choose k solutions. One of these is the right one. I don't know which one. I just have to figure this out. And of course, chances are you're already seeing the solution right now. Okay. One of these is the solution. I don't know which one. So these are all possible hands. There are n elements which are going to be revealed to me. I don't know them. They're hidden. They are going to be revealed in random order. There's a solution I'll maintain initially empty. Good. Now a random element arrives. What does my algorithm do? If my solution covers this random element, I do nothing. But initially it doesn't. First thing I do is I can remove any solutions out here which don't contain a set that covers this set. Out of the remaining solutions, select a random one. This contains at least one set that covers this. Pick that set. So this contained this. One more thing. Pick a random set from this hand. And also pick. This is not the only possible solution, only possible algorithm, but this one is particularly clean in my mind. Okay, good. Next element that arrives, it turns out one of these sets covers it, it's okay. Next element arrives. Now what do? Throw away hands that don't cover this element. Pick a random, I think I did something weird. Yeah. Pick a random hand that covers this element. Or pick a random hand out of the remaining. Pick two sets. One that covers this element, a random one. Is the algorithm clear? So let me tell you the main idea of the analysis. The rest you can, you can't, you'll be able to do it almost yourself. So the crucial question to ask is, do half of the remaining hands cover half of the unseen hands? At least half of the remaining hands cover at least half of the unseen hands. I want to say, this will be a win-win type analysis. Suppose yes. Then what? Then when I pick a random hand and pick a random card from it, a random hand will cover half of this with probability 1/2. A random card will pick 1/k of the elements it's picking. So this will cover about 1/k fraction of the remaining elements. I'm making good progress. It's like that greedy thing that you saw earlier. You are covering about 1/k of the remaining elements in this yes case. Okay. What about the other case? Suppose half of the remaining hands don't cover half of the unseen elements. Then a random unseen element will throw away half of your hands. Because half of the remaining hands are crappy. They cover less than half. So a random draw from here will throw away half of this. So either you halve this and reduce it by constant factor, or you cover 1/k fraction. That's it. The rest is some calculation. I'll show the thing on the slide. In case one, the universe is shrinking. The unknown universe is shrinking. In the other case, the number of hands you have are shrinking. You either learn or you cover. It's a very, kind of conceptually clean idea. Okay, good. And I'm almost done with what I want to say. There's some calculation you need to do, but I'm not going to bother you with the calculation. If you've got the idea, but do ask questions. As long as you're happy with the conceptual idea, I think it's okay. Okay.
So when you pick a random set that doesn't cover anything you need to cover right now, like in principle, there's no need for the algorithm to commit to that now. Is that for?
Yes, absolutely. So you could just put that on the side and say, oh, maybe tomorrow.
But there's something about, so how is this, or like, I don't know if the question makes it like, how is this, or like, is it easier to say like, how is this helping to, or is it just saying that like, this is an easy case and it almost doesn't matter what you do? Or?
So it's helping. So what, Matt, if I just to paraphrase your question, you're saying, look, when I'm picking this random set from my hand, it's going to help maybe later on. So why don't I wait until I need it? So what I could do is I could just wait until an element comes, which is uncovered by my real solution, but covered by one of these solutions one of these sets that I picked only in my mind. So it's helping in the sense that it's covering a lot of elements in the future. So in the future, there are going to be elements that will come that were covered by these sort of future looking sets.
I see. That makes it. Okay, so you're saying it's helpful because it's biasing the distribution of sets that you're using to cover this future element, and you really wanted it to be a random set from this state because from this state it happened to be the case.
Exactly, because I can charge it to the progress I'm making in this.
Okay.
Do you really need to take the first set that covers the current element? Maybe you don't need it, and at the end you will still get a solution.
So you might not need it, but it's easier for a charging argument.
Okay.
And in fact, I don't really need to pick two sets at a time. I could pick, there are various versions of this you can do, but this one is the best one that I can give in one slide. Okay. You can cast this as a potential argument as well and show that this potential decreases, this Lyapunov function, if you wish, decreases every time in expectation, and so the same kind of arguments work. Maybe what I will do is I'll just show you how to make this Pauling time. And some of you know a fair bit about machine learning. and optimization, maybe you can make connections that I feel like there's some connections to be made. I don't quite know how to make it. So here's my algorithm, which runs in poly time, still unit cost. We can also get rid of that, but for unit cost, I'm going to start off. Okay, so here's what I'm going to do. I'm going to maintain a fractional solution. Okay, it's actually a distribution over sets. I shouldn't call it a solution. It's a distribution over sets. Initially, the uniform distribution. At each time an element arrives, as before, if it's covered, do nothing. Otherwise, do two things. Pick a random set from this distribution over set. This is kind of like picking a random hand and a random set from it. And also, for every set that contains this element, up the weight on this set by some factor E. Whatever, E, not just some factor, the E. Base of the natural logarithm, and renormalize to make it a distribution. So just multiplicative weights. That's what I'm doing. Okay. Oh, and this portion might not cover this new element that comes in, so just buy an arbitrary set that covers this element. So this is kind of like picking a, this is the second set that you would pick. And the idea, this algorithm works, and the way we show that this works is that this always reduces this potential in expectation. And it's the KL divergence between my solution and the optimum, plus the number of uncovered elements. So again, I want the same analogy in your mind. Either I'm learning or I'm covering. Either this improves or this improves. This is what I end up showing, that this potential always decreases in expectation. And more or less the analogy with the previous argument is similar. Either this element is covered by a lot by this solution, then our coverage is good, expected coverage is good, or expected learning is good. Okay. And again, there are details here, and there is some proof. Let me not bore you with the proof. It's clearly, I just wanted to show you that the proof is fairly short. And it's just standard ideas. The question I want to ask is, this is morally similar to online learning algorithms that we know and love. But the analogy is not exact. And I would like to make this analogy more rigorous. So if you guys have thoughts on this, I'd love to hear more. Let me skip over all this. Clearly, I have way too much stuff on these slides. Here's what these ideas, this learn or cover type idea works for other extensions of set cover, other covering problems, and some facility location problems not important. I would like to extend this to harder covering problems. So covering integer programs with box constraints. So let me just tell you one particular type of problem that I would like to understand. It's so I want to understand problems of the following form. Minimize some linear function given some covering constraints. A is a non-negative matrix. So A is it's a non-negative matrix, and the rows are coming in one by one. But now this X lies between some 0 and C, let's say. So there's some upper bound, or not, let me not call this C, let me call this B, whatever. So there's an upper bound on what X is. These are often called box constraints. these kind of problems have been difficult to capture in this random order model, and we'd like to understand these. And the whole hope would be just like set cover, online set cover has proved very valuable to understanding online algorithms. I would like online random order set cover to be very useful in understanding random order problems. But I yet don't completely have this sort of grand unified view of the world. We need to understand that. Okay. So I'm going to end here with the thing, set cover. 2 years back, I didn't believe, 3 years back, I didn't believe there was any new algorithms to be found for set cover. We managed to find 2, which are interesting. And in some sense, the thing that I found cute was this sort of beyond worst case perspective was behind these 2 results. I wanted to understand the case of small sets for set cover that gave this local search algorithm. I wanted to understand the random order model that gave this learner cover. So lots of interesting questions. For set cover, can we just close this gap? This, for the complexity theorists, for the die-hard approximation fans, we should nail this problem. And also in the random order model, I assume that the elements are arriving in purely random order. We should, what if this distribution has high mean entropy, high, pairwise independence, k-wise independence, whatever. This purely random assumption is very strong. Can you do something weaker than that? So I guess that's pretty much it. And, thanks so much.
More questions from the panel?
Thanks, everybody.
Can go for him. Thanks again.